All right, guys, welcome back to another episode of Induction 101. Today, we're going to get into some more math, talk about 2-valve versus 4-valve, and a couple other things that we had questions on. Let's do it. All right, guys, I just want to start and thank everyone for all the comments. Really good engagement and a lot of thank yous in there. And I just want to say again, thank you guys for obviously watching. It's my pleasure to try and do this and relay, what little I've learned over the years, and hopefully it helps someone. I'll start with thanking our sponsors, Einstein Motors, and today I'm going to break down a little bit more on some of the calculators we've designed for them and show some real-world examples. Because one of the questions we had in the comments section was, can you show us how these equations work in the real world? And I'm going to get into the Mach index. I had some questions about Mach numbers and low versus high. Darren Morgan's talked about this. I've talked about this for years. Different ports need different Mach indexes. And this is where some people get confused. They're saying, oh, the math don't work as soon as you've got bends and this and that and so on. Once you start moving away from the line of sight, you have to use lower Mach indexes because air doesn't like to turn. It's just like you and me. The tighter the apex at the racetrack, the slower we need to go around it. And that's just simple physics. Air is no different. Air has weight and air has to abide by the physics of the universe, just like we all do. So we're going to cover a little bit of that today. Break it down, and I'm going to start with our first real-world example here, and then we're going to get into understanding why, because another question I had is, Jake, why does your calculator have so many Mach indexes? So I think one of my MCA calculators have from 600 to 710, and you'll see why as we get into it. If we look at some of the equations out there, like Chad Spearson, he's using very low line of sight, so 23-degree stuff where the window is like the short side, top of the short side radius is here, the window's here, so the air's got to go up and down. See it like early Cleveland and stuff like that. Absolutely horrible heads. So guys like that have to be absolute masters at what they do just to try and keep the air from obviously separating off the short turn and creating full-blown turbulence and just turning into a nightmare, and as well as the fuel, balancing that pressure through the bend. And Darren really gets into this probably the best, balancing the right pressure ratio in that port for both fuel and air. But so we're going to talk about low and high Mach indexes. We're going to get into why there's a range and how to look at a port and understand where you should be or what you should target. So yeah, let's go. Alrighty guys, so I put an example on the board. This is one of Tony Knight's combos that we helped develop the manifold for. This is a Holden engine. For those guys in other countries, this is a GM Holden, not a GM American like Chev. It's actually different. This is our own design under the GM banner. So it was originally a 253 and then 308, 304, 355, and we stroked them out to 383 and more. Now we're doing 454s with the aftermarket block. So we just last year did 427 and a 454. Custom intakes and stuff like that as well. And just a quick example, this is sort of what the manifolds look like on the Holdens. As you can see, really wide belly, which allows us to, this is one I've designed for a VN. That is slightly high port, but as you can see, the port is off the floor. The Chevy stuff is, some are as low as 6 mil, where these are way up. The port window is generally higher than the top of the short side radius. So you get a really good line of sight. They can carry a much higher velocity index. And this intake here, I think we've got a 6.1 runner on it. So really easy to get runner length in without getting the runners too close and causing a little bit of cross communication there. So I'll also cover why tunnel rams don't need reversion plates as much as single planes. I think Darren covered this really well. I tagged it in the last video. So we're going to cover some of that as well. But let's look at this example, and I'll show you why the Mach index is so important, because I had some people saying, oh, you know, when you bend and all that goes out the window. It doesn't go out the window. You just need to understand what Mach index to use. The more bends we have, again, the slower the air needs to go, the slower the Mach index needs to be. So this example was originally set the record for the early headed Holden by Pete Murray. So Pete Murray, if you don't know who he is, you should. He's probably one of the best head porters in the country. Him, Tony, and Brenton Marusik would be my top three in any order. They're both absolute gentlemen, and also just, yeah, they know their stuff when it comes to cylinder head design. Especially Tony spent a hell of a lot of time on these heads, trying to get them right, because they are an early 1990s head. And I think they set this record in 2022. I don't know if it's still a record or not. Maybe someone can tell me. I don't follow records and stuff like that. I'm not interested. I don't even talk about my own stuff. I forget about most of the stuff we've been involved because I'm not really interested. Again, I'm a little bit dyslexic and highly functional, so I'm onto other things. I actually had to look this up to remember it. So anyway, so originally, I think Pete said it was like 658. Tony's one come up at 723 horsepower, 7.9. And it also carried torque really, really well. Again, showing how well this port is. Your torque generally will tell you how efficient that port is. 530 foot-pounds even at 7,000. So it's basically a 375, 585. Again, the Holden's like 5.650 something. Someone can put it in the comments. We generally always run a 5.7 or a little bit longer on a 5.85 on these. Bore 430 or 40, somewhere around there. I don't remember the exact bore. Cubic inches around 383. So it's like 381, 382, 383, something like that. And really, really good valve choice, 20616. Again, when we were doing these cast iron heads like 20 years ago, we really got right into, because I used to do 11-second Holden packages and stuff back in the day when we used to do a few street cars and bits and pieces. And the iron heads, I remember, we were cutting some engines back to 202, especially because we weren't at this power level. We were doing 450, 500 horsepower street combos, really, really basic, 10-25 to 1 stuff. And I remember pushing the Holden heads. We were trying to crack, like, I think I was cracking 295. Now guys are getting 300, which is an interesting point, because even Tony's heads, when these finished testing, are only 305 CFM. So this is why I say you can't trust CFM. CFM is not a good indication of mass flow, or how many molecules you're actually getting in the cylinder, because it's not a density measurement. So again, a lot of people have covered this. But basically, what I wanted to show you is the difference between low and high Mach indexes, how to use the calculator. Obviously, I'll go back into the app for that, and how understanding the line of sight will dictate where you're going to be in that Mach index. So if we look at the standard minimal cross-sectional area equation, bore squared, stroke, RPM, the standard Mach of 0.55 works out at 615 feet per second. If we run the numbers on this engine, you'll see it comes up at 273 square inches, which is not even close to this. And that's because this is a high Mach index engine. It's not a small block Chevy. So if we look at, I think Chad Spears, this is one of his equations, I think, or one of the general first MCA equations that a lot of people use. And for the small block stuff, again, because they're a horrible port design, we have to use a lower index, but the Holden isn't. The Holden is, again, it was ahead of its time for what it was, so done really well. So I'm just going to go in now and show you this, how this works. All right, so I'm on the Einstein app or website, and we're just going to go to the Gulp member section and into their calculator hub. And that's the air cleaner I was talking about the other day. I had a question on that about Oh, K&N's pleated. Yeah, that's 100% right. The pleated allows a lower pressure drop for the air cleaner. You'll see it there, pleated K&N. And this is why foam filters do so poorly, because they have far less surface area, so they're going to create more pressure drop. So yes, 100% we calculate for the pleats. That's how we determine the square inches per pressure drop for that calculator. But we'll go down to the MCA calculator, and we'll just punch in this combo first. We've got to go in imperial. So we're going to go bore for stroke 3.75. RPM, not 9,079. There's that dyslexia again. All right, and calculate. Actually, we'll do it at the 620 because that gets us pretty close to the original calculator. So as you can see at 620, that comes up at basically 2.7. So it's pretty close to the original MCA calculator. We'll see what it is at 600. There it goes bigger again. 640. 6.2, but what you'll find, this one is plus 700, so I'll calculate that, and there we go. We're pretty much bang on Tony's numbers there. 2.35 at our MCA. So, and this thing obviously carries velocity really well. So it really is about understanding the port shape to know what Mach index you're actually going to run. And again, this is about the physics of air. This is a dynamic measurement, not a flow bench measurement. We can get into that later. Mean flow factors and velocity, and also flow bench, the standard being 28 inches. But all right. So as you can see, port shape plays a really key factor in selecting our MCA factor, or our index. So, and also I might demo, because we also talked about carburetor size, because Tony thinks this engine will make 750 plus. And when I originally done the analysis, we come in at 730 horsepower. So pretty close to the results Tony got. But my recommendations was twin 825s. And the thing with tunnel rams, and a lot of people seem to miss, they use that Holly calculator, your VEs, which is 0.85. This is why we built a carburetor calculator for Einstein, which has an indexable VE, but we've made it simpler, so you just sort of select street and street strip or serious track and so on. I've moved the VEs accordingly, but I've also put a tunnel ram factor, so you can select tunnel ram. I might show you that in a second. We'll go through and actually calculate this combo just to show you it's not too bad. And again, this is max effort carburetor, so this would be the maximum size carby you'd ever want when you're using my application. So again, you can choose lower values, but you have to be realistic with it. So we have right up until pro stock. So obviously you don't want to select the pro stock carburetor efficiency for a street car. But yeah, I come up at around 730 horsepower, but I think Tony was talking about a few things and the way it carried torque and everything. I think 2.825s, that'll get us up to around about that 1650 CFM in total. And with tunnel ram, because we're putting the shot under the carby, we have really good signal. They'll have far better signal than a single plane wheel. So meaning we can go much bigger in the carburetor without sacrificing a lot of low end response that you'd see normally with a single plane, because they're turning the air so hard and the single gets washed out. And also with a tunnel ram, they generally don't need shear plates or anti-reversion plates. And this is where you'll see a lot of people get confused with over-carbureting dual planes and stuff like that, and dynamic CSA shrinking, and that negative or that bad positive wave getting washed out by mechanisms like that. And the tunnel ram is similar in a way. And I put a tag in the video of Drag Boss's video last week. Darren broke this down really well with the actual shear plates or anti-reversion plates. And again, The tunnel ram will do it naturally because as the air rushes in, we have this extra area in the tunnel ram up around, and some of the serious stuff we start to lay the sides in, and I think Darren talked about this as well. I also get into radius floors. So as I move the runners apart, we have a horrible signal. And I think Darren talked about split carbs, which a lot of the guys got into, and that's so they could get the bore center over the runner for even better signal. Really, really common. But what we've done to trick the manifold for guys that are doing, you know, a street strip engine, they don't have millions of dollars to buy split carbies and stuff like that, we'll actually put a bridge in the middle of the manifold and fairly high, and this helps the air waves separate and feed the cylinders a little bit better, and eliminates that dead area along the floor. Works with the street stuff. We did a couple of big cube Holden. So in Australia now we have aftermarket blocks that'll do up to 454 cubes or bigger, 460 cubes. So we did a 454. I think that went at 830 horsepower, basically a pump engine, and 427, one of the billet Holden aluminium blocks, and then the other one was one of Craig's big Paul blocks, which are really, really good block. We did a 1400 horsepower blown engine with one of Craig's blocks, and a really, really good, solid, heavy block, and they really fixed a lot of the design problems that Holden have. You know, we tested the limitations of the factory Holden block and got to that 950 horsepower and pretty much broke the mains out of it with a blown engine of ours. But so yeah, with the tunnel ram, because we have those negative areas, so as the air rushes in, say on this 4150 flange, we've got all this dead area around the outside, and it acts very similar to what a anti-reversion plate does on a single plane manifold. So as this positive wave comes up, what will happen is in a single plane, it runs up the runner and hits the booster. Now, the whole point of a booster is create a venturi, create a low pressure to help atmospheric pressure push the fuel up into the emulsion tube, into the body, the booster, and that helps atomize fuel. But if we have this positive wave coming back up, we lose signal and we can create all sorts of problems, stutters and all sorts of problems. But with a tunnel ram, because we have this extra area at the sides and we have the hole there, this whole area will be in a negative pressure because we get this string coming in like that. So this is negative pressure here. So any waves that come into the plenum, again, back to our basics in our other video, a high pressure will go to a low pressure. So what actually happens is they get washed out, they get pulled out into the corners, and we get very little signal coming back into the carburetor, but we get a nice clean signal from the runner itself because the runner is much closer to the runner and there's a distance we play with there. But with a single plane, they're coming in and they're turning up, so the signal will never be as good as a tunnel ram, and this is why we go 8 barrels for 8 cylinders, twin carb, and we can get, generally if you do it properly, you'll get the same amount of torque as a dual plane and the same horsepower and better as a single plane. Generally better. We see generally around about 5 to 8% better with a tunnel ram for the exact same thing. Put it on the dyno, it'll make the same foot-pounds, if not better. Generally, a lot of the earlier Holden ones we used to do, we'd build them around the street. So they're only, 550, 600 horsepower street engines, and they were just stump pullers. They're absolutely massive foot-pounds. Foot-pounds that you wouldn't even see with a dual plane, not unless you went super, super small camshaft and they had no RPM at all. And that comes down to the line of sight. The better line of sight, the higher velocity index we can carry, the more torque we can carry. And that leads us into our next thing with bends and stuff like that. But I'll just show you the carburetor calculator real quickly and show you how close we got this one. All right, so I'll get back into the Gold members. We'll go to the calculators. Carby size, here we go. So displacement 383, RPM 7900. We're going to go twin carbs for this, and we'll go a sheet metal race manifold. So again, this is something that's going to be up around the 110% VEs, 108 to, it depends on RPM, obviously. We'll calculate that. So we're coming up at 1681. So as you can see, we're pretty close to that 825. So not too bad at all. And what I was talking about before as cast. So again, if we've got something that's got a few more bends in it, I don't know what this is doing. Here we go. Actually, I'll get rid of that pen. Race port. So this would be something like a cast manifold with a couple of bends in it, maybe, or not quite too great. Its VE count's a little low, as you can see. We're down. So something like this, a set of twin 750s would work great, and then as cast we're down near 1300. So a set of twin 650s would be more suited for this combo. And then again, you can go to carbureted single carb. So we've got street strip, same sort of thing. As you can see, we're down at 900 CFM now for like a 383 street strip type deal. For a mild street, that should drop down there. 750 would be great for something like that. So again, I've just tried to make the calculator a little bit more real world, but again, this is max numbers. So this is the biggest you'd possibly need to make horsepower on that. If you wanted something drivable, you generally pull back, 100 or 200. So on the tunnel rams, we might pull back, from 2 850s down to 2 750s. Might cost us 10 or 15 up top, but we'll make a little bit of torque. They're more drivable. So a little bit of common sense, obviously. All right, again, I'll just finish up on the Mach index, and then we'll get in, cover some other topics that were brought up. So I just thought I'd demo just quickly. So this is what I was talking about when I was talking about high and low, because a lot of people don't understand it. 23 degree, as you can see, really, really low port window. The air's got to come up and go down. So we'll definitely get this velocity gradient. Again, really, really dead floor. And this is something more like the Holden intake. So as you can see, far better shot, better line of sight. So this one's going to be able to carry a hell of a lot more velocity than this port here. So whenever you're dealing with bends and you're dealing with what we call suboptimal induction systems, you have to compensate for that with your Mach index. And I also want to talk about parallel runners as well, which I might cover, and also looking at the complete induction system. But just quickly on what I was talking about with the tunnel ram. So Planum wise, the 4150 will sit here. And generally what I do with our bigger stuff, especially when we're doing some of our what I call a stubby series, so really, really small for bonnet height. Not that I like doing them, but to make them work well, because the runners aren't. So if that's the bore, that bore really should be out here, right? I like 75% of my booster bore to be over the runner, just as a general rule. But if you can't do that, so if we have something like this where we've got a bore there, so these two, what I tend to do is I build a dome in the floor. One helps in a couple of ways, but we're deleting a lot of that dead area that's only going to create turbulence, let fuel drop out of the air and so on. But these ones I tend to leave, depending on how serious an engine is. If it's a street car, I'll leave the sides parallel. If it's more racy, I'll start to tilt them in and we'll start to delete area. The better tuned it is, the less we have to worry about poor harmonics. Yeah, that's a whole nother topic. But and again, if you haven't seen it, check out Darren's video, because he broke this down really, really well. So as these pressure waves are going to come back up, that pressure wave that's going to cancel out our booster signal and create all sorts of problems, it's a high pressure, so it wants to fill in. So these dead areas, which I've gone to the point of filling them in before, I've even fully bogged up manifolds and we shape the hell out of them. They'll get really, really good in a narrow area. and really, really bad in other areas. So you've got to be really careful. This is why some compromises, some square corners actually can be good, especially in a tunnel ramp, because they actually work for you in a way and give you a better, broader horsepower curve. And this is why. Any negative pulses, and you'll see these negative pulses on ITBs. Generally 3 to 4 dips in the power curve. So if you're looking at ITB horsepower curve, it'll, and these are these negative waves that are coming back up, and you can actually see them on the dyno. You watch the pulses, and some of them actually throw fuel out the end of the runner as they're phasing in and out of that. And that's the, I think it's the rarefication, I think that's what they call it, point in the wave cycle where they're basically not feeling the cylinder properly. We've got a positive wave coming up, disturbs the airflow in the runner, and we get a power drop. And because ITB aren't common planum, they can't soften this effect. So when we get it in a common planum, one runner can compensate for the other. This one has a high pressure wave coming out, can help fill another runner, and so on. So this is why common planums tend to make better peak numbers and better horsepower, sort of in that range that we're sort of targeting for. The good thing about ITB is torque on demand, right? We can adjust the throttle, increase the airspeed in the runner. I might have to do a whole series on ITB and talk about even placement. It's something we found that the further we went away with the throttle body, the more horsepower would make ITB, and the more stable that air column was, because the throttle plate actually creates turbulence, or more turbulence, I should say. All air in an engine has what we call micro turbulence, and that's what creates the shear mechanisms and shear time over fuel. It's all interreacting. This is how we create convection. This is how we create our pressure waves. If it was a true laminar event, we wouldn't have any inertia there. So, all right, I'll get this cleaned off, and then we're going to go into some 4-valve stuff, cover a couple of things. I want to cover the parallel runner versus tapered runner, because I see a lot of dyno tests out there. And again, I don't like to say people are doing things wrong, but in induction, we need to understand the whole picture, like from the air cleaner to the tailpipe, because every part affects every element in the system. And I've seen some dynos, and people sent me, so Gary, one of my mates from the States, sent me a video. I think it was Eric Weiner. I really like Weiner's stuff. He's just like hardcore, gets in, back-to-backs, everything, dynos. And he did one with a really big cylinder head that got ordinary, like really started making him question CSA. And I really struggle with these dyno tests, because if it's really hard to put a Paul manifold on, and I consider a dual planar Paul manifold. Sorry, I know guys love them, and yeah, they do great on street cars, but they've got a lot of turns and they've got a lot of dynamic elements in them, and that dynamic CSA. And actually, I might put a video up just now and have a look at this one. So now this is actually a helium balloon in a car, and what I'm trying to get you to understand is there's a huge density factor with air. Air is a spring. I actually heard Darren Morgan talk about a slinky the other day, and this is something I talked about over a decade ago, understanding how if we shake a slinky, how that wave goes down. It's the same sort of effect. We have these density veins moving in and out of the induction system, and the air is like a big spring. And this video highlights how even in a cabin, when you accelerate and go around corners, you can see it's actually going towards the G-force, meaning that the air's getting more dense in one side of the car or more dense in the back of the car. And this is where there's a little conundrum where we say there's a clear correlation between density and velocity. But there's another aspect that comes into it, and that's, I'll try and draw it. It's density. So when I was explaining the runner angle the other day on the small block Chevys, how we'll kick them up, and that tends to make more torque because we get more velocity down here. not only do we get more velocity, and this is where there's a little confusion, we get more density for the same velocity, meaning as this inertia that we created with velocity comes tearing down and we get a sudden change in direction, it's like when you go on a roller coaster and you go down, you feel your guts go right down and your body weight actually increases and you go down and the dip come back up. The same thing's happening with air. So what we're doing is, even though the velocity, we might improve the velocity along the floor, it's going a little bit faster here, we're getting a more dense zone. And we might, this dynamic CSA might take effect. It's probably not a great drawing, but let's say it's something like that. So there's not a lot happening here as far as airspeed goes. And the general rule would be maybe that's in if it's a bit slower, it might be in a higher, or if it's starting to create separation. And this is where I say, is it separation or is it just density thinning? So, and by that I mean is, as this air velocity comes through here, is this air just getting pulled, meaning less dense, not actually to the point of separation? And this is something I think about obviously in induction. And when we look at dual plane manifolds, the carbies here and then bang, bang, we've got a runner like that. So there's going to be a dynamic CSA here, and we might even get some separation there. But at lower speeds, and I actually did a review for Einstein on angles in induction and stuff like that, which we'll probably share in a couple of weeks. And it was some CFD and some real world, I think they call it particle analysis. I can't think of the name right now, but I'm sure I'll put it up in another video. And they were showing how different angles, straight versus curved, affect individual volumetric efficiencies on each cylinder. And it comes down to this, that we're going to get density variations in roughly the same speeds, and due to that inertia, we're going to get different density variations. So this is where, when you're looking at curved runners, you got to understand what's happening with the air, how much more restriction that those curves are creating in the induction. So you look at a lot of OEM, you know, they'll wrap right around because they're trying to get induction length, but they're also creating more restriction. So again, depends on how they'll design it. There's little tricks you can do. I've seen some really, really smart guys out there now actually designing proper air induction systems. So I've talked about this before. A mandrel bend isn't the most optimal bend. So if we have a mandrel pipe in our system, again, this air is going to want to end up over there, again, because of inertia, and we'll end up with this dynamic CSA, all right? And what guys are starting to do now is understand and almost build them like a short turn. So rather than, if we cut the pipe through here, rather than it being around cross-sectional area, it might be something like that. And what that tends to do is slow the airspeed through here and create a better pressure balance. And we look at some of the new Yamaha ports, and they're like that on the exhaust port. Because you've got to remember, they're coming off the head in a turn as well. So what they're trying to do is increase airspeed here, slow airspeed along the floor, and help that pressure front. So if we've got a pressure front running down a pipe, we want that pressure front to turn. The better we can get it to turn together, the less turbulence, separation we could create, the better pressure balance we get through that pipe as well. So, all right, I'll clean this off. That was pretty much it. I want to talk about straight versus tapered just quickly, because again, I see dyno tests, guys on YouTube, and guys sending me stuff, testing runners, and they're testing runner length, but they're testing it in a parallel section. I'll just explain why that's not quite right, and how it can be a bit misleading. Let's do it. All right, so straight versus tapered runners. And again, I had someone sent me one of the videos, I can't remember who it was, but they were testing manifold runner lengths. I think it was on a probably the Ford Modular Mustang or Coyote or one of those ones. And real good engine platform to test runner lengths because they've got a really good port in them, really good straight shot. I've ported quite a few of them. Helped the guys out a fair few years ago with the modulars and stuff like that when they first started coming into Australia. But I wanted to explain a couple of the problems where I see when people are just testing a parallel pipe, because it really is easy to test induction with a parallel pipe because we can just cut it down, weld it back up, get in there, die grind it, most people, whatever, I don't know, just deburr it, hope for the best. And we can do that on the dyno really, really quickly, but there's a few problems that come into that, and I'll try and break it down on the board why it can lead you up the garden path. And there's a couple of telltale signs there, even in the dyno graph with harmonics and stuff like that, that will tell you, yeah, it's coming into tune, but we're actually choking velocity. Because remember, we've talked about two elements here. We have our physical inertia mechanism and we have our harmonic inertia mechanism. And the point is to bring the two into harmony to work together. And a parallel runner won't do that for quite a few reasons. And I've talked about it before. We'll just go through it again. The first being obviously time over distance. This is going to have a hell of a lot more restrictions. So let's say this is 12 inches off the head and this is 12 inches off the head. This runner is going to choke 1,000 RPM earlier. So let's say this is 2.8 and this is say 3.8. We've got a little bit of taper in this one. This runner on the exact same engine is going to choke way earlier, probably 1,000 RPM earlier than the exact same length runner. So what you'll see, and say this is the right harmonic, say for, let's say, a 7,000 RPM engine, and we'll see the dyno curve come up and then go down, and then we get a little kick and then we've turned it off here. Well, that was your harmonic element overriding the velocity track, because this line is velocity, okay? So we're losing volumetric efficiency, and then bam, all of a sudden we see a spike just as we turn the dyno off. And I've seen this quite a few times. Well, that spike was your resonance. That was your harmonic factor. Now, the problem with the parallel runner is we're choking the engine. We're not optimizing that runner length, the point of having the longer runner. So a lot of guys are really just getting poor feedback on the dyno because they're using a parallel runner, not a tapered runner, and they're not harmonizing the two mechanisms that they're trying to make benefit out of. And a lot of OEM manifolds are like this because they're just very easy to cast. They just do them one diameter, and they're more torque related. Again, a lot of people look at OEM, but you got to remember they're really low range engines because they're emission standard. They've got to cruise along at 2,000 and make emissions, where a race engine doesn't. You know, it sort of starts for us at 4,000 or 5,000, 6,000 depending on peak RPM. But and the other factor, so obviously we have too much velocity in a parallel runner, because if this here is at 300 feet per second, so is this. Which also means we're going to get far more wash up into the plenum, which is going to reduce the size of the plenum. So even if you were trying to compare two of the same size plenum, so if this was 100% of engine volume and that was 100% of engine volume, well, that dynamically now is no longer 100%, because we have far more wash coming back up into the intake, far more rubbish signal going into the plenum than this one would have, all right? And we see this with raised trumpets versus floor trumpets, and bigger radiuses versus small runners. I've talked about this in other videos. A tighter radius in a tunnel ram will give better signal to the carby than a bigger radius. We're washing that out, right? But these are factors that we're not seeing when we just use a parallel runner. We're not seeing the on-flow effect, how it affects other elements in the system. So again, we'll have density reduction in this, and that's what we've seen on the dyno, because the velocity is so fast for so long and it's too high. Where this one, you know, say we target that 180, but it's 300 here. We have a our average mean velocity is going to be lower than that one, which means we'll be able to carry this power longer and then use that. But we won't see that because this power curve will just come up properly, all right? So, and then what they do is they cut the runner down and go, oh, look, and now this one goes like that. But they've killed all their mid-range, or they've killed their torque. So you can, again, it's not easy, but we need to look at how to optimize the length harmonically, the volume, and I'll go into a couple of calculators in a second that actually do this with different runners and tapers, and the velocity and how much we're washing out the plenum and how big dynamically that plenum looks to the engine, because this one's going to be throwing out a hell of a lot more. So if it's a biased plenum, if we just have a plenum like that with our 4 runners each side and the throttle body there, well, the air getting to this cylinder is going to struggle. I reckon, if at a quick guess, it's going to be 8% down on VEs in this cylinder compared to this cylinder. And we can run some CFD and see this clearly, that and they don't do weight very well, but even basic CFD will show you this cylinder is always going to get more air. And one of the studies I'm going to post up in Einstein's on exactly this CFD and variable volumetric efficiency per cylinder. And this is a huge problem, obviously, even in tunnel ram tuning when we're trying to dial in each cylinder, because if you're reading average air fuels at the collector, one might be 14, one might be 11 to 1. So this is where it's really, really important to get your carby spacing right. This is why with some of the super stock and really, really quick drag races, we'll actually offset the carby plate. Which is hilarious, because they actually look horrible on the dyno. They won't do well, but at track they'll do well. So we'll just use a small block Chevy for the moment, and say that's the runners, and here's our barrels. Ideally on the dyno, this is sort of where we want it, right? Because obviously the fuel's going to fall straight down, and we're going to get fairly good signal. Obviously there's going to be some jetting needed, but what we do is with some really, really quick cars, we'll offset the top plate, and now these are in front of the runners. And the reason we do that is because we're fighting G-force. The fuel, just like a blower tends to throw to the rear, the fuel is going to fall because the fuel is heavier, 100 times or whatever it is, heavier than air. It's going to want to fall backwards slightly. So we actually offset the top plate slightly. Again, we'll lose horsepower on the dyno, but at the track, you'll pick up a few mile an hour. So, but yeah, that sort of thing really sort of annoys me in one way, because it's giving guys really not a good idea of what is optimal runner length, because you're using a parallel runner, which is time over restriction. It's more restrictive. We have a thicker boundary layer. We have higher averages. So you're changing all that. So this is why we've got to look at the total induction length, the averages, the plenum, the wake, the airspeed at the top of the plenum, because all these little things change your end result and won't give you good feedback. And again, I was talking to a guy about exhaust, and he said, oh, I'll just dent the exhaust. It'll make no difference. I've seen it on Engine Masters. I think that's the ones they had 4 dyno pipes they put on the engine, found the closest one and dented, and actually made horsepower. And then the conclusion was, well, dents really don't matter too much. And that's totally false. And the reason why it's false is simply that, one, they didn't spend the time. They didn't spend 3 weeks like I've done making an optimal pipe, finding the best size for the pipe on the dyno, finding the best step, and then denting it. They just found an average pipe that worked better. But what it told them straight away is when they dented it, I think they ended up making more horsepower. And this is what I had a quick look at it. And that told me it increased velocity. So velocity was never targeted properly, meaning the pipes are actually too big. Hence the dent helped them increase velocity, improve that scavenging mechanism, and that's why it made horsepower, not the dent didn't matter. It was the pipes were never right to start with. So we've got to be really, really careful what we take as gospel out there and say, again, I don't know it all, and there's guys out there far smarter than me, but we've got to think about some of the mechanisms that we're playing with and why we got the results we did. And things like this, I think people are missing the bigger picture. Same with carby size I've talked about on dual planes and stuff like that. And you get that shrink in dynamic CSA, so you get a better signal for longer. So you can tend to overcarb them a little bit more so than on a single plane. There's a lot of factors that come into it, but we've got to understand the whole system. Dyno pipes versus street pipes. We see this time and time again. A dyno pipe will like a big exhaust, a street pipe won't. The Cleveland was a good example of this. 4V versus 2V, one like the big pipe, one like the small pipe. Again, down to the scavenging and airspeed out of the exhaust. So, all right. So we're going to move on now. Hopefully that helped it. Again, I'm rambling a little bit now. Could, just go on for hours about this sort of stuff. But I want to cover a couple other topics and then we'll call it a day. All right, let's do it. All right, so we're going to lead into a bit of 4-valve stuff, but I thought I'd cover one other element in a really, really good induction system, good, a factor that I have termed the Gulp factor. Basically what that is how much air obviously the manifold's going to drink, and this will lead into some of the calculators I'll show you now. And that's basically the primary induction length having around 92 to 95% of the cylinder we're going to fill. So, and that's why I call it a gulp theory. So each time the piston pulls down, it's going to gulp that amount of air. And the closer we get to that 92, 95%, the better it seems to be efficiency-wise, because we're only replacing the runner pretty much. So if we just took round numbers, said 100%, then all the air is already in the chamber, basically, for the chamber. Like, you know what I'm saying? So all it needs to do is replace, and then this section fills that section. So this tends to give us the least amount of restriction because all the air is in the runner. The motion's going to take off fairly quickly, and the air in the plenum basically just needs to refill that runner or thereabouts. All right, I'll show you some calculators now on runner volume and stuff that I've generated for Einstein, just to make this sort of stuff easier to know where we're at, and then we'll cover some 4-valve stuff. Here, I'll just try and find that one. Oh, yeah, here we go, runner volume. So this one basically is similar to the other calculator. You can find included angle, so we'll just do the same thing. 285, 4.5 on a 6-inch runner. And now this will not only give us our angle, I did ask about, but minus, same thing. It gives us our pore volume of the actual runner. And this is really, really critical information, especially if you've got your port at 280 cc's. You can add these two together. And I also have a full primary induction length where you can calculate the full volume as well. So you can put in your average CSAs and your port length, plus your runner length, plus your plenum opening, and it'll calculate the whole velocity and it'll calculate the whole volume of the primary induction length and the average CSA of the total induction length. But as you can see, this calculates the average in the runner at 3.675 CSA and gives us a pore volume of 361 cc's or 22 cubic inches. I think that's it. Yeah, this is a 4-valve induction volume one as well. So remember I was talking about I'm more of a 4-valve man, so a lot of my calculators, original calculators around 4-valve stuff. This is one here. And I've also made it really easy with this stadium, round, oval, rectangle windows. So rather than you getting in there with paper and counting the dots, you can just, like a stadium, so you obviously know what a stadium is. That's like a 2J or a Honda port or something like that. A rectangle with 2 radiuses at either end. So then we basically, all we need to do is put the width in. So if we've got a 50 mil by say 32 mil high, so 50 mil wide, like a 2J, I think they're 55 something, but just use rough numbers here. And then we can put in what I've found, I might show my my tool that I use to measure all this, but what I've found the easiest way to measure the 4 valves up is basically just do your height. So let's say, or the width is between the divider and the outside wall. So 25 mil, let's say our height's say 26 mil. And then you can go in and feel each radius. So I measure each radius and say it's, up the top, we'll say 8. I like a smaller radius on the roof. And on the bottom, I'll have maybe a 16 mil radius. Again, this is probably asked about. I'll go the other way, but you'll get the idea. And then you can put your valve size in, your stem size, because it'll subtract the stem from the valve, and your throat ratio. Then we can put in our port center line. So let me see, this is metric. So we'll say the port's 4 inches long, and we've got a 6-inch long runner on top of that. And the plenum opening is 2,000 square millimeters. And then we'll go calculate. Now this will do the whole lot for us. This will do us our entry. This will do our single divider area, as you can see, our total divider area, our single throat ratio, our total twin valve throat area right there at 2 square inches, our average port CSA, our total average induction, our port volume and our runner volume, and our total induction length of 9.8 inches or 250 mil, and our total induction volume of 369 cc's. So again, I use all this data for my twin cam stuff. So there you go, guys. That's the introduction. Maybe we lead in next week to a little bit more twin cam stuff, and we can go through a few more calculators that are built around it. One I'll show you just really quickly, and this obviously upsets a few. Here's another quick one, just Windows CSA. Same thing, guys. You can pick, and with the rectangle, you can go in and fill in your corner radiuses, metric or imperial. Now, I did ask about this when I built it because it does need a decimal place, and I wasn't sure if people would struggle with 0.375 is 38 and so on, what the conversion would be. So we do a AFR, and they're roughly 2 high, 125 wide, and they'll have a 375 corner radius in each. And the reason I've done it independently is because a lot of the new cylinder heads will have different radiuses in different corners, so tend to have a bigger corner radius on the floor side, a smaller radius up on the far opposite corner, and then this will just calculate our port window, 2.63 square inches. And then, as I said, you've got oval in here, you've got stadium for the 4-cylinder stuff, circle obviously, which is easy, 2-inch, calculate, done, 3.14. So, and our the twin cam average flow limitation one, this is a really good one for our twin cams, and this sort of calls a lot of people out. Again, I've got a 146 factor. That's pretty high. That's like maximum. So what this calculator will do is say we've got, we'll just take an RB for example, 34.5, 6 mil stem, 88 throat ratio. At the best flow factor we possibly can, we can say the head flow 300 CFM. And this will call BS to a lot of, especially in the twin cam twin cam scene. There's so much BS out there around flow figures and stuff like that, because again, they haven't realized that CSA is the driving factor, not what the flow bench tells you. So now this will calculate everything from the single valve area, stem area, our combined throat area, and it'll give us our max theoretical flow potential at 314. And it will give me a flow coefficient factor of 95%. But realistically, we should be using a 136. No one's getting up near a 146. So 136 is a more realistic factor for, especially a 1990s cylinder head. So we'll calculate that. As you see, that gives us a theoretical of 2,9 3 CFM. So when you see guys claiming, you know, standard valve flowing, you know, 320 CFM, you can pretty much call BS, because they are sort of exceeding the laws of physics there. So even at 300 CFM on a street head with a 34 mil valve, we would really need maybe a 1 mil over at sort of 35, 5. We'd want maybe max the seed out at 90. I've gone to 90 and a half, 91, but I don't really like doing that, especially on boosted applications. And you can see that's a little bit more realistic now, 326 CFM at 92%. So these are my, obviously, 4 valve calculators that I use, and I've built a fair bit of data around, so that gives you a bit of an idea. Maybe we can lead that into next week's one, where we'll do a little bit on the 4 valve stuff. All right, guys, so we'll leave it there. I'll catch you next week. Again, we'll probably lead into 4 valve stuff and maybe a few more questions and bits and pieces. I've probably missed half of what I wanted to talk about in this now I'm thinking about it. But again, there's so much to cover. There's so many areas, and my mind goes 100 miles an hour. So I've really just sort of winged this one. I had a couple of ideas I wanted to cover. I'm pretty sure I covered them. We've broken down basically the difference between slow and fast Mach indexes in ports, and some critical areas we obviously have to look at, and some critical thinking that we need when looking at dyno tests that we see online, whether the person's catching everything or what the results are actually showing them. Yeah, that's about it. Thanks again, guys. See you next time.